So hello everyone, we begin by knowing and learning what is an electron microscope. An electron microscope is a scientific instrument that uses an accelerated electron beam instead of light to form a highly magnified image. Unlike traditional microscope which uses light and are limited by wavelength of light, electron microscope is able to achieve an astonishing level of details when are scanning through specimen at an atomic scale. It was developed in the 1930s by Ernst Ruska and Max Knoll. Due to the invention of electron microscope, scientists are able to visualize structures that were once unimaginable, such as atomic lattices in materials to the finest detail of viruses and proteins. Next, we take a look at some of the electron microscope contributions to humanity. Some includes enabling discoveries in nanotechnology, molecular biology, and semiconductor engineering industry. Industrial impact, we can see that it is critical for quality control in electronics, metallurgy, and pharmaceuticals. In medical advances, it enables cryo electromagnetic has revealed protein structures essential for drug design. And in forensic, it helps to solve crimes by analyzing microscopic evidence like fibers and residues. So, in summary, electron microscope bridge theory and practice, reshaping modern science and technology. As mentioned earlier, electron microscope contributes greatly to the human society and therefore are indispensable to various industry. Since electron microscope uses an accelerated electron beams as a medium to scan through specimens, it operates on the basis of wave-particle duality and resolution. Since electron behaves as both particles and waves, it, it, uh, it follows the de Broglie wavelength, which is shorter than visible light, therefore increases resolution. Now, these resolutions are sub-nanometer scale or atomic scale that allows it to be visible to human eyes. However, it does requires high vacuum to prevent electron scattering.
Okay everyone, now I'm going to present to you the type of electron microscope. The first one is transmission electron microscope, TEM. The principles and the capabilities of this microscope is electrons transmitted through the ultra-thin specimen of the stage and image formed by electromagnetic lenses, and the image reveals internal morphology, crystallography defects, and the resolution is about below 0.1 nanometer, which is atomic lattices. The only limitation for this microscope is it's so complex. It's great complex sample preparation. And the next one is scanning electron microscope, SEM. It's all about surface imaging and 3D visualization. It focuses electron beam scan surface in raster pattern, and it produces secondary and backscattered electron, high depth of field to 3D appearance, versatile for bulk materials. Resolution is about nanometer range, lower than transmission electron microscope. There are also some advanced variants or modern developments in the electron microscope, which is in STEM, combines transmission microscope and scanning microscope, enables imaging and compositional analysis. For cryo-EM, preserve biological samples in native state, near atomic resolution of proteins and viruses. The microscope can also revolutionize structure, biology, and drug discovery. Key system in electron microscope is electron gun, electromagnetic lenses, vacuum system, detectors, and sample preparation. For the details for electron gun, it's such as thermionic versus field emission, and for the lenses, it's such as magnetic fields for focusing. For vacuum system, it prevents scattering. For detectors for scanning microscope, it's secondary and backscattered, while for the transmission microscope, it's fluorescent screens or digital cameras. Sample preparation for transmission microscope is ultra thin slices, while for scanning microscope is conductive coatings.
Now, let's look at how microscopy and nanoscale analysis are applied across different fields of science technology. First, material science. At the micro and nano level, we can study grain boundaries, dislocation, and phase distribution in material. These help us to understand mechanical strength and durability, basically why some material are critical for busted. Second, application of nanotechnology. Moving even smaller, nanotechnology focuses on nanoparticle, nanotube, and quantum dots. These tiny structures enable breakthrough in electronic medicine and energy storage. They are so critical for creating advanced nano device and sensors that make modern technology faster and smarter. In biology and medicine, microscopy reveals the ultrastructure of cell, organelle, and viruses. Techniques like cyro-EM allow scientists to visualize protein structure, a key step in drug development. This drive progress in virology, oncology, and molecular biology, helping us understand disease at the molecular level. Finally, semiconductor industry. Microscopy ensures precision, and quality control. It used to inspect integrated circuit and detect nanoscale defect, ensuring reliability in microchip and processor, the foundation of all modern electronics.
Alright, for applications in forensics and failure analysis, for practical investigations, we have the trace evidence such as gunshot residues, fibers, and contaminants. Like the example we have here, which is the example of gunshot residue, which is used using the electron microscope. Another one, we have the engineering failures, which involve fractures, corrosions, and analysis. We have the example of corrosion analysis, image in the right. So all of this is to support law of enforcement and industrial safety. All right, for the advantages, we have three advantages. The first one we have is the time management. So for time management, we have the extraordinary resolutions and magnification to shorten the time for us to see the amount of quality and detail of the thing we want to observe under the microscope. For experimental errors, we have the analytical capability. And for in future improvement, we have to enable visualization at atomic scale. For the limitations, we have three limitations. For the first one, we have the time management. As of time management, we have the high cost of acquisitions and maintenance. For the electron microscope to be detailed and not having any failure. For the experimental errors, we require trained personnel to guide the user to use the microscope in the correct way. And for future improvement, we have the complex simple preparations. For future developments, we have the first one, which is the data collections. In terms of data collection, we can use AI-assisted imaging and automated analysis by using any AI like ChatGPT and Gemini. For the second one, we have the result analysis, atomic resolutions advancement with minimal aberrations. In conclusion, portable and hybrid system for wider accessibilities. Last but not least, we have the conclusions. For key takeaways, electron microscope transcends optical limits. TEM, SEM, STEM, and Cairo-EM each serve unique roles. Applications span material science, nanotech, medicine, semiconductor, and forensics. Despite limitations, future innovations promise broader accessibility and atomic scale precisions. That's all from us. Thank you.